Hi, this is Hossein Mohit, and welcome to the From Design to Relational Implementation video lecture. In this lecture, you will learn how to convert your conceptual designs like class diagrams into the relational implementation schema. So just please note that the lecture is only for review of the material. So in order to be good in your exams and also assignments and quizzes, it is essential for you to read the book and completely do all the assigned tasks and assessments. Class diagrams or conceptual models generally provide a more accurate and complete representation of the business processes and their complexities. Additionally, they can easily be handed over to programmers working on the application layer of your overall system design. However, there are a few systems that allow you to directly implement these conceptual models and class diagrams into the database schemas. You will need to translate, transform, or convert them into a relational database schemas to make them ready for implementation. And remember, if this transformation process is done correctly, assuming the conceptual model fully represents the business, you will automatically achieve the fourth normal form in your database design. So let's review the process of transforming base classes. Base classes are standalone entities. They are not part of the superclass, subclass, or a specialization generalization relationship, and they are not created to handle many-to-many relationships. In other words, they are not association classes. To convert these base classes, standalone independent classes, you need to follow following steps. Step 1. You need to use the base class name as the relation or table name. Step 2. Use the base class attributes as the relation or table attributes. And the third one, which is so important, add the necessary primary keys if there aren't any defined. For example, transforming a sale class might look like this. You create a sale table with sale ID as the primary key, along with attributes like product name and amount. So as you can see, the sale ID might not have been in the original class diagram. It wasn't designated in the original class diagram, so you will need to add it in this stage. Now let's discuss how to transform a specialization, generalization, or superclass-subclass relationship into a relational schema. So first start with the superclass. This will be the base class. For example, person. You would create a table for person and person ID as the primary key and convert the class attributes into table attributes. Then, for the subclass like married person, you will create a separate table. In this case, the married person table, the married person table will include person ID, spouse name, and any other subclass specific attributes. However, there are two common implementation approaches for this one. The first approach, you might create a married person table that contains person ID, social security number, name, address, and other shared attributes. But notice that many of these attributes are already present in the person table. So it's gonna lead the data redundancy. This would violate normal forms, so you need to avoid duplicating these shared attributes. The second approach, instead, you will implement the married person table with just person ID, which serve as both the primary key and the foreign key linking to the person table and the spouse name. This way, both the person and married person tables share the same key without repeating the attributes, ensuring that there is no data redundancy. The goal is transforming superclass, subclass, or generalization specialization classes to use the same key for both table and avoid repeating attributes in the subclass except for the key. Alternatively, you might choose to implement the subclass attributes directly in the superclass as additional attributes. For example, you could decide to include spouse name as the attribute in the person table. This decision depends on the specific requirement of the system and should be made in the consultation with the developers. With experience, you will learn when it's more beneficial to keep subclasses separate versus merging subclass attributes into the superclass. When transforming tables within one-to-one relationship, you need to insert the primary key of one entity as the foreign key attribute in another table. To establish this relationship, the primary key in one table becomes the foreign key in another table. Here is an example. We know that each customer can have 0 or 1 checking accounts or 0 or 1 saving account. But if there is a checking or saving account, it must be associated with exactly one customer. This means that the bank or financial institution does not allow shared accounts. Here is how this can be implemented. Customer table. You will have a customer table with customer ID as the primary key. To simplify, we will remove other customer attributes for now and focus on customer ID as the key. Checking account table. You will have a checking account table with the checking account ID as the primary key. This customer ID will serve as a foreign key to establish the relationship with the customer table. And the last one, saving account table. Similarly, the saving account table will have saving account ID as the primary key, so customer ID as the foreign key to relate to the account to the customer. This approach ensures that each checking or saving account is linked to exactly one customer, maintaining the one-to-one relationship. To convert one-to-many relationship, you need to insert the primary key of the one side, the side with the cardinality of 1, as the foreign key on the many side, the side with the cardinality of many. For example, let's say each customer can have many checking accounts, but each checking account must be associated with one customer. Here's how we can transform this. So the first one, customer table, it's gonna have the customer ID as the primary key, as you see. The checking account table, the checking account table will have checking account ID as the primary key. The customer ID will be included as the foreign key in the checking account table to relate the account to the customers. So the customer ID serves as the primary key on the one side, the one that's related to the customer, and becomes the foreign key on the many side, the checking account. This setup maintains the one-to-many relationship, ensuring that each customer can have many checking accounts, but each checking account is associated with only one customer. As you have learned in the past, many-to-many relationships are generally discouraged in the database design. In fact, I call them cardinal sins. They cannot be implemented as they are, and I also recommend not having them into your conceptual design at all. You should start addressing many-to-many relationship at the conceptual design stage by breaking them down into the one-to-many relationship, like the one that we learned in the previous sessions. Once you break the many-to-many relationship into two one-to-many relationships, you will need to intermediate table called intersection table or association class. This table creates the necessary link, turning the many-to-many relationship into one-to-many and many-to-one relationship. For example, let's say the bank has changed its policies and now allow shared checking account. This means that each checking account needs at least one customer associated with it, and each customer can have zero or many checking accounts. Here is how we can transform this many-to-many relationship. The first one, the customer table. So in the customer table, we start with the customer table and give it a customer ID. For the checking account table, we move to the checking account table and assign it a checking account ID. And the third one, which is the intersection table or association class, we can create this table to link the customer and checking account tables. We will call this table, we name it as a has checking account. This table will contain two foreign keys, customer ID and checking account ID, which together they will form a composite primary key. This setup ensures that we adhere to normalization rules and avoid violating any integrity constraints. The has checking account table only needs the fields necessary to create a link between the customers and uh, checking account tables, effectively breaking them down the many-to-many relationship into the one-to-many and many-to-one relationship. In the has checking account table, the foreign key is customer ID, which references the customer table, and the foreign key checking account ID references the checking account table. Together, these two fields create the composite primary key for the has checking account table. This way, you would ensure data integrity and proper normalization within your database design. If you have a well-designed conceptual model that includes a many-to-many relationship between two classes, you will likely have an association class as well. For example, consider the relationship between students and courses. Each student can enroll in many courses, and each course can have many students. To manage this, we create an enrollment table to store information on which students are enrolled in which courses. The enrollment table will have unique rows for each student course combination. Additionally, we may have an extra attribute such as grade, which tracks the grade a student has received in each course. So in this example, the enrollment table is not just for resolving the many-to-many relationship, but also to store specific information like the grade related to the relationship. So here is how you can transform this conceptual design into a relational schema. The first one, a student table. The student class will become a student table with the attribute like student ID and name. The course table, the second one. Similarly, the course class will become a course table with the attribute like course ID, course number, and course name. While course numbers may be unique within the school, it is generally a good practice to have the automatically generated internal ID like course ID. This one helps prevent potential conflict if course numbers aren't unique over time. The third table, enrollment table association class. The enrollment table will hold both a student ID and course ID as the composite primary key, representing the many-to-many relationship between a student and courses. And In addition to the key, the enrollment table will include the grade attributes, which is the specific to this association. So the foreign keys, the student ID is the enrollment in a student ID in the enrollment table will serve as a foreign key linking the table to the student table, and the course ID in the enrollment table will serve as a foreign key that linking the table to the course table. So by following this approach, you ensure that many-to-many relationship is properly broken down into two one-to-many relationship, and also it would avoid any data redundancy and integrity issues. Now let's discuss how to convert or transform recursive relationship into a relational schema. Recursive relationships occur when a class has different rules within itself. For example, in employee class, employee can also be a manager or supervisor. From a logical perspective, a manager is also an employee, so this creates a recursive relationship where the class is related to itself. Here's how you can transform these kinds of relationship into the relational schema. The first one, employee table. Start by defining the employee table with employee ID as the primary key. Then add other attributes like first name, last name, phone number, and hire date. The second one, handling the recursive relationship. The challenge is how to designate which employees are manager or supervisor. So you cannot simply add another employee ID column because it would violate referential integrity. All attributes within the table needs to have the unique and meaningful names. Instead, you can introduce a new attribute such as supervisor ID, which represent the manager or supervisor of the employee. The supervisor ID is recursive foreign key because it references the same primary key, the one that we have here, employee ID, within the same table. So the supervisor ID points to the employee ID of the supervisor or manager within the same employee table. For example, if employee ID is 1520, as you can see in the table, employee ID is 1420, and also sorry. So if the employee ID is 1520, say supervised employee ID is 1420 and 2920, then the supervisor ID for those employees, which is the 1420 and 2920, will be 1520. So the key thing to remember is that this recursive foreign key doesn't have to be unique, meaning multiple employees can have the same supervisor and then the same supervisor ID. So in order to make sure that we already meet the referential integrity, the supervisor ID column ensure that the recursive relationship is properly managed without violating referential integrity. It refers back to the same table, but because it's a foreign key, this value don't need to be unique. By following this step, you can transform recursive relationship into relational schema without violating integrity constraints, ensuring that the relationship between employees and their supervisor are clearly defined. Once the relational schema is ready, it's time to implementation. During implementation, you will need to define column or attributes, constraints such as the data type, such as integer or character, the value range, the domain, whether the column can allow null values or not. These constraints must be carefully decided and implemented to ensure data integrity and accuracy. At this stage, you will also write the SQL code to create the table. The SQL keyword Create table is used to define and create table in the database. If you need to delete an existing table, you can use the drop table command. Here is an example of SQL code to create a customer table. We start with the drop table if exists. This is useful when you are working with a database that has already been implemented and you want to make sure that you are creating a fresh table. However, before dropping a table, you should always back up your data to avoid losing valuable information. Next, you use the create table statement to give the table a name and define its attributes. For example, the customer ID is an integer and it cannot be null because it will serve as the primary key. For the first name, we define it as a character type with the length of 30 characters, and it also cannot be null as well. We follow the same process for other attributes defining their types and constraints. Note that the value type like char or char and varchar or varchar are the DBMS dependent, meaning that each database management systems or DBMS may have its own specific value types. For instance, if you are working with SQL Server, you need to use the value types specifically to the SQL Server. If you are using the MySQL, you need to know that the value type used by MySQL. And if you are using the Oracle, you will have to familiarize yourself with the Oracle specific data types. Although many general value types like int, char, varchar, or etc. are common across the most DBMS system, it is important to check the specific requirements of the DBMS you are using. After defining each attribute and its constraints, it's time to define the table constraints, such as the primary key. For example, you would explicitly designate the primary key for the table. However, foreign keys are typically not explicitly defined in this part of the SQL code. They are often discovered and managed by the DBMS based or relationship data relationship between tables. Before we finish this chapter, let's quickly review the standard data types used in the database management systems DBMS. Keep in mind that there is no guarantee that these types will be exactly the same across different DBMS platforms. So you will need to consult the specific documentation for the systems you are using. INT or integer typically refer to the integer or whole number. For example, in Microsoft Access, you would select number when defining primary keys. CHAR or char or varchar are used to represent alphanumeric alphanumeric string data. Char 30 refers to the fixed length of the alphanumeric string that is just 30 bytes, meaning it will always reserve 30 bytes of the space regarding the actual length of the strings. For example, the varchar 50 allow for the variable length alphanumeric string up to the 50 bytes. If the string is only 25 bytes long, it will only use the 25 bytes of space, making it is more flexible and efficient in the certain cases. Dates time is reserved for representing the dates and time. And the last one, numeric, is used for the numbers with the decimal rather than whole numbers. And it's in some DBMS systems, you can also use decimal to specify the exact decimal numbers. Again, remember that different DBMS systems may have slight variation in how they handle these data types. So it is important to refer the documentation for the systems you are using. Okay, so this concludes the short lecture on how to convert your conceptual design into relational schema and proceed with an implementation. Remember, this was just an overview of the process. To fully grasp the details and nuances, it is essential that you read the book and dive deeper into the material. Have a good one.